In this lab, we will use the built-in temperature sensor that is inside the microcontroller to measure its core temperature. It's a pretty common thing, actually. Many microcontrollers have a small either band gap or some bad diode, which is put in a circuit in such a way that, when you heat up a semiconductor, the amount of charge inside the material increases, and so it starts to conduct electricity better. And if you cool it down, it decreases and resistance increases. So many of these microcontrollers have some temperature sensor inside with which you can either measure the core temperature, or if the microcontroller is sleeping a lot, after you wake the microcontroller up, if you quickly measure the temperature, then it's basically the temperature of the ambient uh, air. So you can use it like a small, not very precise, but functional temperature sensor. So um, let's look at the datasheet of our development kit's processor. And you will find information about the temperature sensor. So on the datasheet, let's go to electrical characteristics, and under analog to digital converter, there should be information about temperature sensor. So here it is, thermometer output gradient. So basically, the manufacturer of these chips has built in a temperature sensor which changes its voltage by minus 1.92 millivolts per degree Celsius, or it is minus 6.3 analog to digital codes per degree Celsius when you have voltage reference 1.25 volts. So I will also draw it down. And the idea is that the temperature sensor is built in such a way. Here is temperature, and here is, let's say, ADC codes. And basically, it's something like this. We don't know where this point is or anything, but we know that the angle of this slope is such that basically the tangent of this is minus 1.92 millivolts, or, well, since I put ADC points here, I better change it from millivolts to ADC points, so it's minus 6.3 ADCs per degree Celsius, or per Kelvin. So we know the slope of this line, but we don't know how high or low this line is. And the manufacturer, during the manufacturing of this chip, they actually do a calibration, and they write the calibration values in a special place in flash memory, which cannot be overwritten. They just burn the calibration data in, and you can read it from software. So let's check out again our microcontroller's data sheet and reference manual. And let's look at memory and bus system. I think it was here. So inside the flash memory, there is a special place in flash memory called DI, or device information. It contains many things like unique ID and version of this chip and so on, but it also contains calibration data. So let's try to find more information about this device information page, which is available in many microcontrollers, not just Silicon Labs controllers. So here it is, device information page. And these values are read-only, so you cannot accidentally override them. I think you cannot, but maybe you can erase the page. I don't know. Anyway, here are some calibration values for analog to digital converter. You know, when it's produced inside the chip, it is not perfect. It's a little bit off. So during the manufacturing, the chip is put on special test bed, and it's some software is run through it, and some measurements are made, and this calibration register contains values that you can feed into analog to digital converter and cancel out this manufacturing mistake. And actually, Silicon Labs library loads these values automatically when you run this analog init, this analog to digital converter init or single init, I don't remember which one it was. But here you can see when you initialize a channel, a load calibration data for selected reference is done automatically inside the software. So if you, this is why for Silicon Labs chips, it's good to use their drivers and their code, because they have put it in. If you, for example, don't want to use this software, you want to write your own libraries, well, then you have to remember also to load the calibration data from flash memory, right? But in this case, the Silicon Labs programmers have already included this feature in their drivers, so I'm using them and I don't have to worry about it. I don't have to remember it myself. As you can see, here's information about analog to digital converter calibration, digital to analog calibration, and so on and so on. But here is also two addresses which have information about temperature. As you can see in this address, calibration temperature 0 or calibration temperature is written. So when the chip is calibrated, basically the machine measures the chip temperature. It is usually just 25 degrees. So probably the number that's written here is just 25, but maybe the room is a little bit colder, maybe it's 24 or 26, but the temperature is burned into this memory address. And then, and at another memory address, it says analog to digital converters value read at 1.25 volt reference. So they set up 1.25 volt reference, and they just read what the temperature sensor says. So in our picture, the slope of this line is fixed because it is determined by the material that's used in temperature sensor, but the offset is kind of determined by analog to digital converters precision and some other factors, so it changes. And in these calibration registers, they basically say that at some temperature written in this analog to digital converter calibration temperature 0. So at this point, maybe I can write it down. At this temperature, which we can read, the analog to digital converters value was this. So it's done like this, and the value is written in this register called analog to digital converter 0, temperature 0, read 1 volt 25. So here, I'll copy it. So let's put it like this. Okay, so and this is the calibration point. The slope is fixed. So with this information, there's only one line that exists that goes through this point and has this slope. So basically, that's enough information for us to use some basic arithmetics and algebra to write an equation where we sample analog to digital converter signal at some other temperature. I don't know, let's say currently there's 30 degrees Celsius. We do the sampling, and we get some analog to digital converter value. And we can calculate what the temperature is because we have calibration data. Okay, so now let's write some code which does it. And also, using the internal temperature sensor is actually very, very simple. If we go to analog to digital converter description, then basically the temperature sensor is just one of the inputs of analog to digital converter's positive side. So we have the analog to digital pins from pin 0 to pin 7, which is in this processor port D0 to port D7. And the next input is temperature sensor's input. And here you can actually check out that there are also other inputs as well. For example, supply voltage divided by 3. So you can set reference to 1.25, then you can sample supply voltage divided by 3, and from this ratio you can calculate what the supply voltage is, right? So the chip can measure its own supply voltage. And here are some other values like power supply, ground for offset calibration, voltage reference divided by 2 to measure linearity. If you select voltage reference divided by 2, then the output of this should be 1/2, right? And if it's not, then you know that there's a little bit offset. And also you can connect digital to analog converters outputs. Maybe it's necessary for some signal processing and so on. But basically, instead of analog to digital converters pin 7, we will select temperature sensor input, but everything else will almost stay the same in our analog driver. So I will create a new function. I will call int 8d analog get temperature. Or better name would be get core temperature, so that we know where this temperature sensor is located. If the chip is under heavy load, it will heat up by itself, and the temperature will be higher. So this is not ambient temperature sensor, but the core temperature sensor. And actually these chips, they can heat up on their own by several degrees, maybe by 5 or 6 degrees when they are loaded to maximum speed and maximum calculations and so on. So you don't need a huge heat sink for it, but just realize that they do heat up. So let's see, analog get core temperature. And now let's write implementation for this function. So to make analog to digital converter sample temperature sensor, we don't have to change analog to digital converters general settings, but we do need to change the channel settings, because as you can see in channel settings, we select the input. Here we would use, instead of input channel 7, we would select input temperature or something like that. It will be called similarly. And also we need to change the reference. The calibration was done at 1.25 volt internal reference. So we should use the same reference also here, okay? So basically what I need to do is I need to copy this code, channel setting structure and initialization function. I copy it, I paste it in my analog get temperature. And here, first of all, I need to change reference. So I control click on this reference, and I have here analog to digital converter reference 1 volt 25. I copy it, I go back and paste it here. Resolution 12 bits, and input channel, I control click on this. Then I have to control click on this. And this takes me to all the possible inputs that this analog to digital converter supports. And here we have temperature. So analog to digital converter, single input temperature. which is in register is just number 8. It's input number 8. It's wired inside the chip in such a way that it's input number 8. But I copy this beautiful name. I go back and I paste it here. And I'll change the comment. So this basically acquisition time 1 is fine. 1 volt 25 reference, 12 bits, and input is temperature. And we initialize the analog to digital converter 0 with these new channel settings. And the second thing that we have to do is basically just sample this thing. We can copy sampling code from our analog get light level. Just these 2 lines. Analog to digital converter start, start single, wait until it finishes. And when it's finished, then we can read out the value. But the value will be just some analog to digital converters, number. So in our case, I will read it out to int 32t ADC result equals to analog to digital converter data single get. I'll copy it from here, or I could type it. So we read analog to digital converter's result into a variable. And then we have 2 options. We can use floating point numbers in some algebra formula to convert, or we can use integers. But in our case, since this is a powerful microcontroller, we could also use float. Okay, so how can we convert this data into the value? So one thing that we can do actually is we can go to mlib, go to Giant Gecko. Here are some energy aware drivers, one of which is temperature sensor driver. Let's see, is it the correct one? I think so. Basically, the reason why I want to mention this temperature sensor driver is that in example code, or okay, let's first check out if we have some example code for this in Simplicity Studio, because actually they have some bug in silicon that in some versions of this chip, they need to actually put an offset to the analog to digital converter value. Okay, I'll show you it in the following way. When you work on a microcontroller, you have selected your wonderful microcontroller and you want to use it. Before you pull the trigger and use that chip, please go to the chip's Errata document, because there is this document where they have manufactured many of these chips, and then they realize that there is some mistake in the chip. So you definitely need to check out in Errata document that maybe exactly the feature that you want to use has some bug, right? It's possible. So let's check out this Errata document and see if there is some problem with the chip. And well, because I work with these chips very much and very frequently, I know it. As you can see, there is an offset in analog to digital temperature sensors calibration data in revision D of the microcontroller. So if you happen to have bought revision D version of this chip, then unfortunately the analog to digital converters temperature sensor calibration data has a small offset. But the guys in Silicon Labs have noticed it. And maybe there's also a workaround with which we can fix this silicon bug. And as you can see, it says workaround exists, yes. So you can also check out other errors on this chip, but you don't have to panic that I'm teaching you some stupid chip that has many mistakes in it. Almost all microcontrollers have some silicon bugs and some mistakes in the code. Mm, I know only one chip which has zero bugs, right? But it's a pretty old chip. I don't recommend using it anymore. Uh, it's just one certain chip. So what we have here is the offset is burned into chip with um, a bit wrong way. Then we have time base not wide enough, requirements for analog to digital clock over 7 megahertz. In our case, it runs exactly at 7 megahertz, so we don't care. Then byte order not working, and AES not working, something like that. Backup real-time clock errors as well. So as you can see, there are some bugs. So you need to check them out before you use certain functionality. And the good thing is that many of them only exist in the first version of the chip, but with each revision, uh, most of them are, fixed. For example, there's no offset anymore. There's no time-based problem anymore. So only few of these problems remain. So let's go to this offset thing. So in this Errata document, I just click on it. And here it is, offset in analog to digital converters, temperature sensor calibration data. The ADC temperature sensor calibration value stored in device information page has an offset equal to 112. I don't know why, but basically what happened was they measured the temperature, and when they burned it into the chip's flash, somehow 112 got subtracted. And that's it, okay? So when we convert temperature from analog to digital converter to degrees Celsius, we just have to check out if product revision values are 16 or 17, we need to use analog to digital converter temperature read minus 112. So they have accidentally added 112 to this value. But it's simple algebra. We don't have to worry about it. And let's write this code with an appropriate fix. Okay, so basically what we need to do, so in our driver where we write this analog get core temperature, as I mentioned before, we need to read out the calibration temperature and also the value. So in memory and bus system, under device information page, there is this address in flash memory where the calibration temperature 0 value is stored. So let's try to read it. There are two ways we can read it. We can just copy this address. Also, let's call the variable with this same name. So it is, it's 7-bit variable. Sorry, 8-bit variable. So we can basically use unsigned 8-bit integer cal temp 0 equal to value pointed by unsigned integer 32-bit pointer and this address. Sorry, this. Or since the flash memory is organized in 32 bits, maybe it's safer that if we use 32-bit variable. So unsigned 32-bit variable calibration temperature 0 equals to value pointed by unsigned 32-bit integer and this pointer address. So basically this reads the value from the address. However, there is a more beautiful way to write this. Instead of this address, because maybe on a different chip, it's located in a different address. Silicon Labs have created a structure for this, which is written in the following way. They have created a virtual device information page structure, dev info, and you can access its members through arrow pointer. And here you can find all of these values. So we need this cal. Okay. And if we control clicked on this thing, then its address will actually be there. I think so. Okay. And the example code that is used by Silicon Labs is even more sophisticated, because maybe it has, some offsets. In this case, it's bits 7 to 0. So maybe it will work this way. But I'm just having this example code that they have, and they write it a little bit differently. They write it like this. So they read the cal info, but then they end it with calibration temperature mask, and then shift by calibration temperature shift. That's interesting, because the mask is 0x00ff0000. But in the datasheet, they basically say that it is 7 bits. However, yeah, now I get what the problem is. If we wrote it with a pointer, it wouldn't work, because this address ends with 2, but the memory is organized in 32 bits. So actually, we are not able to read from this address, most probably, because its flash memory is 32-bit wide. So we would actually read these both numbers, and we need to extract this upper part from that address. So actually, Silicon Labs have an example code where they give this line. So we actually need to copy it. So we read from calibration register, and then we clear unnecessary bits, which are actually these CRC16 bits. And then we shift it by 16, and this is the line. You can just copy it from me. And the next value is calibration value. I can copy this thing like this. So, and it is as you can see, bits 15 to 4 are the reading, and 3 to 0 is reserved. So again, we would have to remove bottom 4 bits. So I will create unsigned 32-bit integer with name ADC temp 0 read 1 volt 25 equal to, and again, I will just provide you the code that is offered by Silicon Labs, and they say that the correct way to write it should be this. So it is reading from analog to digital converter 0 calibration register 2. It is probably this. And then extracting the corresponding part, which is for temperature 1 volt 25. So it is easy to make a mistake here if you don't have Silicon Labs example. You could have found this information if you just started a new project from Silicon Labs, selected that you want to use the starter kit, and here should be a internal temperature sensor example. So if you use the internal temperature sensor example, it has the lines that I'm writing to you right now. So you would have found them as well. So with these two lines, we read the temperature and that thing. And the next thing is we will introduce float variable called temperature gradient, which is equal to, let's take it from the datasheet, minus 6.3. Okay. And there are many ways to rewrite this formula in such way that we get analog to digital converter value at some other temperature. But to save time, I'll just write it in front of you. So let's use floating point numbers. It will be a little bit easier on us. So let's use this as float, but then we need to cast it as float. Oh, sorry. Do I need to cast it? I don't think so. So let's just write float temperature equals to calibration value, calibration temperature 0 minus calibration value, the one that we read, minus our sample, and divide by temperature gradient. But we can leave it as int 8t. This is the temperature, and we return the temperature value. So this is how we can calculate this temperature. Zero. So temperature value here minus analog to digital converter result. This variable could have been integer, but we don't want to lose some fractions, so we will write it this way. So this value minus this value is the difference, and we divide by temperature gradient, and then it's subtracted from calibration temperature, and then we get the result. I'm not sure why I need this. Okay, so let's test the code out. However, we also need to fix the analog light level. So when we initialized analog init, then we loaded channel with the settings for light level sensing. So now we need to move these to analog get light level function, so that when we want to sample light, we load the channel with light level measurement settings, and we do the analog to digital conversion and return. And when we want to do temperature sense measurement, then we initialize channel to temperature sensing values. Then we do the sampling, then we read the calibration, then we calculate temperature and return temperature. So now let's check out if this code actually works. I will go to main code, and here I print light level, and now I will write print f temperature equals to %d new line, and comma, and analog get core temperature. Let's try to build it. Check out if no mistakes in the code. Okay, 25K flash size. So why did flash increase by 25 by 3 kilobytes? Because this chip doesn't have a floating point unit, so operations with floating point numbers take quite a bit of space. I think previously, yesterday previous lab, we had flash size something like 21 kilobytes. I added these floating point number functions, and so the flash increased by 3 kilobytes. The reason is that floating point number arithmetics on regular processors without floating point unit take a lot of space because they're done in software with a lot of code. But well, this chip has a big flash, so we don't care that much. So let us try this code out as it is. I flash it to device, program, and let's check out. So it says temperature, something's wrong. Temperature is off. So let's check out what the problem is. So the example code, oh yeah, maybe this thing is product with revision 16 or 17. We didn't put code for this errata fixing. So product revision is written also in calibration in device information page. ADC product revision is somewhere here. So product revision is in address 0x0fe081ff. We can read it from there. And let's write it here down. And I'll just copy the code from example. So it's like this. We create a variable product revision, which is equal to device information, page, part, number, address, and product revision mask shifted by product revision shift, because the flash memory is organized in 32 bits, so we can only read addresses that divide by 4, and then we read actually this whole thing down, and then we just extract the top part. As you can see, it is masked with FF0000000, and then shifted by 24. And now we need to write the code if prod revision equals to 16, or if it is equal to 17, if it's true, then we need to do one of two things. Either we subtract from calibration 112, or we add 112 to our analog to digital converters result. So here they say in the errata that you should subtract 112 from this value. So we read this value here, but I'll move it a bit higher like this. And one more bracket here. Okay, so we read the calibration value, and if product revision is 16 or 17, as it's written here, we need to use this value minus 112. So this value minus 112. Then we read calibration temperature, then gradient, calculate. I don't know. Let's try. Maybe now it will work. Let's see. Something's still not working. Possible reason is that there could be some problems with these floating point numbers and stuff like that. So I'll go back to the example code. 17 like this. Okay, let's see. So we need to find what's wrong with this code. Let's see, maybe something's written in reference manual. If we go to analog to digital converter, we need to check out what is written about temperature sense. I don't know where I can find it. Somewhere in the data sheet. And here it says temperature measurement. Analog to digital converter includes internal temperature sensor. So it is calibration and device information page. Datasheet, select 1.25 volt internal reference, measure the internal temperature sensor with 12-bit resolution. Here's how the temperature can be calculated. Oh, here is actually the formula. Calibration temperature 0, calibration temperature 0, minus analog to digital converter 0, temperature 0, read 1 volt 25. Yes, minus analog to digital converter result multiplied by voltage reference divided by 4096. This basically translates to this gradient, and we have it. The minimum acquisition time for the temperature reference is found in the electrical characteristics of the device. Let's go back to datasheet, acquisition time. So probably the problem is that we have acquisition time equal to 1, but maybe it's too fast. So the temperature sensor, again, we switch on the temperature sensor to measure it, but maybe it hasn't stabilized yet and we already are sampling. So this is why maybe we have a wrong result. And they say that we should find this acquisition time in electrical characteristics of the device. Okay, let's try to find it. Acquisition. Maybe it will be somewhere here. I don't know. Well, unfortunately, nothing is found. This is acquisition time for analog to digital converter. Required acquisition time for this voltage reference doesn't help. But in the example code that Silicon Labs provides, they are using acquisition time equal to 32. So now let's check out. Maybe that's the problem. Right now it's minus, it's showing wrong temperature, but I changed the acquisition time to 32. I flash it. And wow, now the temperature is, reasonably good. So it says 27 degrees. I will put this thing now next to the laptop's fan. And as you can see, the temperature is going up a little bit. 29 degrees, 30 degrees, and so on. Okay, so it looks like it works. And to maybe show you a little bit, bigger difference, here's my development kit, here's the chip, and I'll blow some hot air on it. It's set to some like 100 degrees. So I'm blowing the hot air onto the chip. but I'm holding it away. I don't want to destroy this board. So I'm blowing it up, and as you can see, the temperature goes to 44 degrees, 45. Maybe it would be safer that I blow on the opposite side so that the LCD screen is not destroyed. As you can see, I'm heating up the bottom side of the board with hot air, and the temperature is going up 52 and so on. This is actually a good feature. Um, in my experience, we had manufactured some devices, and we noticed that some of them didn't work well. The client complained that the device becomes unresponsive, doesn't work, doesn't reply. It was a remote control device, and fortunately, we had a possibility to send a firmware upgrade to the device, and we upgraded in such a way that it started to use the internal temperature sensor of this chip, and it started to report the temperature. And what we found out was that the client had actually put the device in a very hot place, um, next to some kind of heating appliance, and the temperatures inside the device got something close to 90 degrees. But actually, if you look at the datasheet of these chips, you will see that the chips guarantee the temperature that it can, you know, uh, survive in is only 85 degrees, right? In reality, if the chip is heated to 100 degrees, it might still work, but um, there's a risk that, within a 1 year or 2 years, the chip will just malfunction and not work. But the chip overheating to 90 degrees wasn't the problem. The problem was that the device's power supply overheated. And all modern power supplies have built-in temperature protection. So when the power supply overheats, it automatically internally shuts down to avoid, setting itself on flames. All of these DC-DC converters have a temperature control built in. So when the device gets really hot, it just shuts down and cools off. And only after it has cooled down, it only then turns on. And so we caught our client to actually misusing our device, putting it in a too hot place. And then when we told them that, they moved the device to a warmer place, not so hot, to some cooler place, and the device worked for many years. I don't know, I think it's still working. So this internal temperature sensor may help you find such cases where somebody is using the device in the wrong manner. So now I stopped heating the device, and the temperature drops. Now it's only 34 degrees and so on. Okay, so let's go back to the code and let's check out what we did here. Oh yeah, actually, I need to show you one more thing. So in this lecture, you learned about the existence of Errata document, which is available for all chips, and you need to inspect it before you use the chip, because maybe exactly that one feature that you want to use has some bug. So maybe you want to use a little bit different chip. And we also learned about calibration registers. Many microcontrollers have such thing, calibration registers, from which you can read calibration values, and then you can improve the performance of your device. But now let's look at one more thing. So first of all, maybe um, usually we want to get rid of the floating point numbers if we don't need them. If we check the datasheet and we check out the precision of our temperature sensor, it's written here analog to digital converter. Let's go to the temperature sensor, and here it is. thermometer output gradient, minus 1.92 millivolts degrees Celsius. What is its precision? I'm not sure if I can find it in this datasheet, but I can swear that I have seen this information in different other datasheets, which basically says that the precision of the internal temperature sensor is only maybe something like 1 degree, plus minus 1 degree. If you take, if you build 100 devices and take them to the lab, their temperatures will be plus minus 1 degree in precision, right? So one device will say 26 degrees, another will say 24, some other will say 25, and so on. So the temperature sensor is not meant to be extremely precise and extremely good. So there's no need for us to calculate the temperature with 5 numbers behind the decimal point, because actually it's just plus minus 1 degree. So this is why there's no problem that we rounded up the temperature to full degrees. We have integer instead of float for temperature, because we can accept a number without decimal places here, because it's not that precise. How can we get rid of other floating point numbers such that we don't lose the the precision and the calculation for this? So what we have here is the formula that I will rewrite in Paint. Cal temperature, so it's temperature degrees is equal to cal temperature minus, and here analog to digital converter 0, temperature 0, read 1 volt 25, minus ADC result. Okay, I'll just leave it ADC temperature minus ADC result divided by this temperature gradient, T grad. So right now, actually, this number is integer. This number is integer. Yeah, so, and also this number is integer. I don't know why I used float here. It was in the example, but I'll use int. And here I will also use int initially. Okay, so let's build it and let's check out if it works. I think it should. Okay, it works. So using floating points there was actually not necessary. Next up, when we subtract one integer from another integer, the result is integer. So this part calculates to integer. However, when we divide integer with float, the result, the first integer is automatically upgraded to float and only then divided. Because if we divide integers in C programming language, integer operations are always truncated or rounded down automatically. Basically, we just take the whole part of the division, and so we would lose the precision. If we set the gradient to be integer, it would just lose this 0.3 part, and the result would be, quite a bit off, 10% off at least. So in C programming language, these numbers are automatically upgraded to the highest level. So integer divided by float, integer is upgraded to float, float divided by float is float, and then we subtract from integer float. In that case, either the integer is upgraded to float and subtracted, or float is downgraded to integer and then subtracted, because when we subtract, if the result is integer, then we lose the fraction anyway. But there's an easy trick, ages old trick, how to get rid of floats. So if this thing gradient is 6.3, actually minus 6.3, what we can do is we can just multiply top and bottom of this fraction by 10. And minus 6.3 times 10 is equal to minus 63, which is not float. This is just integer. And this top part multiplied by 10, integer multiplied by 10 is still integer. So, however, when we divide them, since top and bottom are multiplied by 10, these 10s would cancel out and the result would remain the same. So basically in our code, what we can do is we define this number as integer, the second number as integer. The t grad I will change to integer, and from 6.3 to 63. And before dividing by 63, I will multiply top by 10. In this way, this number is multiplied by 10. The top part is multiplied by 10. In C programming language, the order of things is from left to right. So first, these numbers are subtracted because they are in brackets. Then they are multiplied by 10. And then they are divided by 63, which is 10 times the gradient, and we will get the same result, except it will all be with integers. And to make it even better, a good thing is to write, instead of int, which we don't know the size of, we should use int 32t. So this will be int 32t, this, and also this. And now calibration temperature is int 32. This thing is int 32. This thing is also int 32. And this t grad is int 32. And now we don't have any floats left. By multiplying top and bottom by 10, we got rid of it. And now let's build it. And as we can see, the code size was reduced quite a bit. It was 25 and something kilobytes, and now it's 24 kilobytes. So we saved 1 kilobyte with this. Let's flash it. Maybe it doesn't work. Let's see if it works correctly. So as you can see, the temperature is calculated correctly. And actually, not only did we save 1 kilobyte of code, we also made it work much faster, because integer multiplication is hardware supported in the core, and integer division, maybe it's built in, and even if it's not built in, integer division is much faster than floating point division in software. So this code actually also performs faster. So this is a trick that everybody uses in microcontroller embedded programming, since the chips usually don't have floating point unit. And even if they have it, it's more expensive. People just try to use integers instead of floats. And as we did here, it's usually pretty easy. If you have some floating point coefficient, you just multiply it with so many tens until you get rid of the point. And the top part you also multiply by the same number. The only thing that you need to check out is that the multiplication doesn't overflow the top part. But analog to digital converter is 12 bits. If you multiply by 10, you add only 3 bits. So you don't get over 32 bits, because ADC is 12 bits plus 10 is 2 to the power of 8, approximately 2 to the power of 4. So you add no more than 4 bits. So you get a 16-bit number. It's smaller than 32-bit numbers. So everything works brilliantly. And the result is the same. So let's go through the code so you can see it. You can type it down, compile, check that it works, and then upload on Errata so that I can see that you did this lab. Let's check out all the code. So in the main code, we only added this printf temperature, %d, new line, analog get core temperature. And in analog.h, we added analog get core temperature function prototype, which is int 8t, which is 8-bit integer. It can be plus or minus, but it only has 8 bits. And in analog.c, we moved the light level initialization channel code from init to analog get light level. So it was moved. And here in analog get core temperature, we created this function which samples the temperature, uses calibration data, and then outputs result. And the reason we use 8-bit instead of 32-bit integer is it's smaller, so it takes less space in memory. And the temperature, for example, 8-bit integer's value can be from minus 128 to plus 127. The temperature will never, for this chip, go over 127. So we can use a smaller integer. Okay, so type out this code, compile, check that it works, upload, and we see ourselves in next lab.